everybody. My name is Jerry QU. And before we begin, does anybody know what this is a photo of? No one does. Okay. So basically, this is a photo of the cast from CSI. Everyone knows what CSI is, right?
Yeah.
Okay.
Yeah.
So I'm going to begin off with like a story about when I was 12 years old, a long time ago. And basically, I was watching my first episode. I was watching my first episode of CSI, and I was amazed by all the technology that was used in forensics, in like the field that they were exploring. And I was really amazed by what they were doing. But what I remember more was after watching the show, reading all the internet reviews about the show, a show that is so technically deficient that they thought that Visual Basics was the industry standard for pinging an IP address. That's crazy, right? Visual Basics isn't even a thing anymore, right? Microsoft took it away, and they thought that this was the industry standard. So people laughed at this show, and people were amazed by how deficient they were, but maybe we don't give them enough credit, because they got one thing very right. One of the most iconic and infamous scenes in this show had to do with image enhancement. Image enhancement is basically taking low-resolution images and converting them to high-resolution images. And when this show introduced that, people laughed at them because they thought it was impossible. You can't create pixels out of nothing. But today, we're using neural networks to turn images like this into this. It's amazing what we can do today with artificial neural networks. And we're pushing the boundaries of what we thought were impossible the day before. So for example, here we can see that convolutional neural networks are being used for object recognition. Furthermore, generative adversarial neural networks are being used for converting low-resolution images to high-resolution images. We're also using recurrent neural networks to predict what text will be typed in next for a sentence. And this is amazing how far we're pushing what we thought was impossible yesterday. The future is now. So even though neural networks are so ingrained into what we use every single day, most people still understand how they work, and even more don't understand how they actually learn. So we're going to be looking into that for the beginning of this presentation. This is a perceptron. It was invented in 1950, and it consists of nodes. As you can see, there are three circles there, x1, x2, and y. Those are called nodes. The two on the left, x1 and x2, they're input nodes. The one on the right, y, is an output node. Basically how information runs through the system is numbers get passed through into the nodes x1 and x2. They then get multiplied by the weight represented by w1 and w2 respectively. They then get summed up along with a bias, and they get passed into the node y. At y, they then get passed through an activation function, which back then would probably be a heavy sidestep function, which basically outputs either a 1 or a 0, making it easy for binary classification. That's what they used back then. And that's how information basically passes through this very simple precursor to the neural network. Fast forward to today, and we have the neural network. And these basically work in much the same way, except it's a complete network of nodes instead of just 3 nodes. However, you still have weights between the connections between the nodes. Those weights, by the way, are randomized when you first set up a training session for your neural network. You still have a bias and you still have activation functions, but those have advanced a bit since then. For example, we have the sigmoid function, we have the ReLU function, we even have the leaky ReLU function, as many of you probably know what those are. And we use them now today for better accuracy and to do a lot more than we could before. So how does information pass through this really basic neural network? Well, as basically the same as the perceptron, we input values into the input layer, they get passed through, and this is called forward propagation. So now we basically understand how neural networks function. How do they actually learn? Well, neural networks learn, at least some of them learn, through something known as the delta rule, which is basically a form of performing gradient descent or optimization. Just like, let's say, if you're the CEO of a business, what you want to do is you want to optimize the profits in relation to the sell price of your inventory. So you want to maximize your profits in relation to how much you're selling all of your items. It's the same with neural networks. What you want to do is you want to minimize the amount of error you have in relation to your weights in between all of your nodes. And for example of what an error would be, let's say you want your neural network to multiply your input by 4. If you input a 1, well, then you tell it that you want to have an output of 4. But as I said before, the weights are randomized. And let's say it was randomized to 3. If you inputted a 1, it would output a 3. And obviously there's an error there. There's a difference between what you expected and what the actual output was. And that's basically what an error is. That's what we're talking about. How does this work in actual neural networks? Well, basically we take the target output at a specific node, we subtract our actual output from that specific node, we then square it in order to emphasize larger errors as well as make sure that all errors are positive. And then we take the summation of all of those errors in the output layer. And we divide by half so we can easily find the derivative of this. Now, this equation is just for one iteration. But in a neural network, we want to, when we're correcting a neural network, what we really want to do is represent the network as a whole. And so one iteration isn't really helpful. What we want to do is to apply many different iterations into this. And so we take the summation of the sum of squares of many iterations called an epoch or a training session. So how do we actually change the weights in a neural network in order to make it learn? What we do is we take the derivative of the error at each node in relation to the weight at that node. And that basically gives the rate at which our error changes in relation to the weight, the rate at which our error changes in relation to the weight, and then we can decide how to adjust our weights in relation to that. So let's look at an example to make this easier to visualize for people who aren't as experienced in neural networks. Let's take an example where we simply want to multiply our input by 2. If we input a 1, then we expect an output of 2. If we input a 2, we expect an output of 4, and that's what we tell our neural network. But since the weights are randomized at the beginning, it might be 3 instead of 2. And in this case, if we inputted a 1, we would have an expected output of 2, but since we have a weight of 3, we would have an actual output of 3. And this means that we have a sum of squares error of 1. If we repeat this for an entire epoch, as you can see up there, we can see that the total sum of squares error was 30. Now, if we increment our weight by a tiny little bit, by 0.0001, in actuality, this would be much less as we're finding the derivative. But for visualization's sake, we're going to look at this. You can see that our sum of squares error actually increased by 0.006. And this means that as we increase our weight, our error increases. And so logically, we should decrease our weight. And that's basically what we're doing when we're finding the derivative of our sum of squares error in relation to our weight. Okay. And this is a graph visualization of that. If you have a positive derivative, it means you should reduce your weights. And if you have a negative derivative, it means you should increase your rates as to get closer to the global minimum. Okay, so how do we actually change our weights? What we do is we set the new rate or set the new weight to our old weight minus our derivative multiplied by our learning rate, where the learning rate is just simply a predefined value which is normally extremely small and defines how fast we want to train our neural network. It's normally small so that we don't have massive changes in our weights as to create chaosity in our system, but it's also normally big enough so that our system doesn't fall into a local minimum. You know what that is. Okay, so how does this apply to actual neural networks? We've been abstracting things so far. We've just been multiplying values. But in a real neural network with multiple nodes, what we would use is a process known as back propagation, where basically we find the partial derivative of our sum of squares error at each node in comparison in relation to each weight of each input into that node. And that will allow us to figure out how to change our weights accordingly at each connection. So now that we all basically understand how neural networks work and how they learn, let's look into the implications of the implications of neural networks on society and students like myself who are going to be in the job field in the future. Okay, so a lot of people are worried that if we develop neural networks to become extremely advanced, we will lose a bunch of jobs. People are worried that if we use generative adversarial neural networks to create lifelike images, we won't need visual designers like this person anymore. People are worried that if we can make neural networks that can talk to people like customer service representatives, we don't need people who are customer representatives anymore, and these people will lose their jobs. And even some people are worried that if we can create neural networks that can create other neural networks or create other programs like Google's AutoML is doing right now, then we don't need programmers anymore. That is simply not true. I don't believe it's true. Because neural networks and innovation, or AI in general, they create more jobs than they take away. And this can be illustrated through a simple example about the printing press. The printing press was a massive disruption to its industry. People who used to write books or who used to write newspapers, those people lost their jobs. but also created jobs for people who operate the printing press. And as this new innovation made books and newspapers cheaper, more people could buy them and the demand increased. And so companies had to increase the supply, and so they hired more people. And in the end, more people were hired than people fired. And so as you can see, it was better overall for the job market. Applying that to today, you might see people, for example, customer service representatives, losing their jobs to neural networks. But we're definitely going to see an increase in technicians or electricians or programmers who can operate or maintain these new neural network systems. I do definitely believe that in the future, people who have white-collar jobs, where they work at an office or in a cubicle, that might be a major decrease. There might be a major decrease in that field for people with that job, because normally these can be fairly easy to replace, for example, an accountant or customer service representative, and these people take up a lot of space and resources that can be easily replaced by a neural network in a simple server with people operating on that. But this is definitely not set in stone. What I'm speculating on the future might not be what actually happened. Just as we saw at the beginning of my presentation with like CSI, people didn't believe, people thought it was impossible to generate an image like that, to up the resolution. But looking at today, we can do what we thought was impossible a couple of years ago. And applying that to what we know today, we might see something impossible happen in the next couple of years, and we can't really predict that. As for students, in students right now who are going into the job market later on, I definitely do not believe that students are being prepared for the future job market. It's because schools aren't teaching students what they should be teaching them. They're teaching students concepts that aren't really applicable to our world today, but were applicable to the world yesterday, or aren't applicable to our future world. For example, schools are teaching students how to optimize a quadratic function from completing the square, but they could be teaching students how to find the derivative of a function and do that even simpler, but teaching them something that's applicable to a real world. For example, the derivative is used in the delta rule, and it's a good concept for people to learn as it's actually applicable in our world and in the future. Also, schools are teaching students how to use Visual Basics, something that is actually obsolete now because Microsoft isn't even launching that anymore. They could be teaching students about Python, which would probably be fairly similar to teach, and then they could also expand that by giving them examples in neural networks or motivating to do more in that. But overall, students aren't being prepared for the future world. Students aren't being pushed from a young age. Students aren't being taught the right concepts. And students probably won't know what to do in the future when the industry has changed, when everything has changed, when neural networks and artificial intelligence has been implemented, and it is not like it is today. And this isn't just students, this is people in general. People must change to fit what the future job market will be like. Just like people who used to write books or used to write newsletters before the printing press, they lost their jobs. And people who operate the printing press, they got a lot more jobs. And so we really need to create jobs. We need to train people to fit the jobs that will happen in our future. So I hope you are all ready. And you obviously are, since you're here at this conference right now, because the future is now, and so we should be ready. Thank you.